Hello everyone. In this video we are going to talk about measuring and monitoring volatility, and then I'll mention about EWMA, GARCH and value at risk, parametric and non-parametric methodologies here. Let's begin. Our first chapter is quantifying volatility, guys. Quantifying volatility. Why this is important for us? Because fatality fatality is important for us, and then we need to know before starting implied volatility or estimating volatility here. Fatality refers to distribution with a higher probability, guys. Okay, higher probability. Fatality another mean is higher probability of observation occurring in the tails relative to the normal distribution, guys. Okay, normal distribution. And then a distribution is skewed when distribution is not symmetrical. Okay, a distribution is skewed when the distribution is not symmetrical. All right, not symmetrical. This is a normal distribution, guys, and then this is not normal distribution. I sorry for drawing, my bad. This is not symmetrical and not bell-shaped, guys. All right. Maybe it has a like a shape it here, and then this is left skewed, and then if he's have a like this shape, this is right skewed, guys. All right. In model risk, a number of assumptions are necessary, and if the parameters of the model unstable, they are not constant but vary over time. Okay, but vary over time. For instance, uh this is a normal distribution, guys. Okay, this is really bell shaped and normal distribution, but guys, uh this is a this is a fat tails, guys. All right, fat tails. This is more high probability here. All right, this one, sorry, this one normal, but orange is fat tail. Okay, fat tail. Another chapter is division from the normal distribution. Fat tail are most like the result of the volatility and mean of the distribution changing over time. Okay, the second possible explanation for fat tail is that not second moment or volatility is time varying. Okay, time varying. This explanation is much more likely given observed changes in interest rate or volatility, maybe interest rate volatility, increased market uncertainty following significant political or economic results in increased volatility of the return distribution, right? This is really important to know fat tails. Then we have regime switching here. This is important. Regime switching, guys. Regime switching. Regime switching volatility model assume different market regime exist high or low volatility. All right. Maybe a market have 8 volatility, but maybe B market have 15 volatility. This is the regime switching, guys. Different market or different observation market regime have different volatility. and the probability of large deviations from normalities such as fat tails occurring are much less likely under regime model switching model because it captures the conditional normality, guys. Okay, captures normality, conditional normality, I mean. For instance, this is volatility, I mean sigma, and then this is t, time, and we have some actual and regime here. If we have like this volatility here, I really driving back. Sorry guys, I really driving back. This is a uh sorry, this is a regime. This is regime. Oh no, sorry. This is the actual volatility. This is a actual volatility. And this is our uh this is our regime, guys. If we have difference here, this is regime switching. All right, guys, this is our regime switching. And then maybe we're gonna have estimating value at risk. Maybe we desire estimating value at risk. We have historical based approach. Historical based approach. Historical based approach. This is typically fall into three subcategories here, guys. Three subcategories here. One of them parametric. Second one non-parametric. Last one hybrid, guys. Hybrid. What is parametric approach here? What is parametric? Guys, this is delta. Sorry. Delta normal approach in valuate risk. This is a really good calculation method. And then non-parametric method is historical, guys. Okay, historical approach. And what is hybrid? Why we calling why we call it like a hybrid? Because we are using weighted historical simulation, guys. Weighted weighted historical simulation. What does that mean? Weighted average or weighted historical simulation. Guys, this is EWMA and GARCH. Okay, EWMA and GARCH. And the implied volatility based approach, we have another subcategories here. This is our subcategories. And then another one, implied implied volatility volatility based approach. Okay, implied volatility based approach. This is uses derivative pricing model, estimate implied volatility based on current market data rather than historical data. And maybe you know we have Black-Scholes and stochastic and non-stochastic, I mean econometric model to estimating implied volatility. And we have non-parametric and parametric approach here, and we have some advantage of parametric method here. Non-parametric model does not require any does not require regarding entire distribution of return to estimate var. Okay, no require no require no require assumption regarding entire distribution return estimate value at risk, guys. All right, this is our big advantage in non-parametric versus parametric. This is a non-parametric advantage, guys. Okay, another one non-parametric advantage is fat tails, because fat tails and skewness and other divisions are not are no longer concern in estimating process. Okay, fat tails and skewness are not are not concern sorry concern estimating process, guys. This is easy. We have also disadvantage here. Of course, we have disadvantage here of non-parametric method. For instance, data used more efficiently with parametric method than non-parametric method. Okay, data is more efficiently using here, and separating of the full sample. This is another advantage. Sorry, disadvantage. Separating full sample data into different market regime reduce amount of usable data for historical simulations, guys. Okay, data are data amount usable for historical simulation. And then implied volatility, for instance, implied volatility. What is implied volatility? First of all, what is implied volatility? Implied volatility is estimating future volatility using historical data. Requires time to adjust current changes in the market, guys. This is really easy sample. Uh, if we want to estimate the future volatility, we need to using historical data. Requires time to adjust current changes. An alternative method, of course, we have an alternative method for estimating future volatility is a implied volatility, guys. Okay, implied volatility. Maybe you know Black-Scholes method is used to infer an implied volatility for equity option process, and the implied volatility model reacts immediately to changing market condition, guys. Okay, changing market condition. This is BSM model. Um, estimating volatility. Uh, estimating volatility. Another important estimating. Sorry. Estimating volatility, guys. The traditional measure of volatility requires the first measure of change asset value from period to period, guys. To period estimating volatility. This is traditional measure of volatility. And then we have formula here. U E I and S E minus S E minus 1 over S E minus 1. Okay. S1 12 and S0 equal 10, and then U is equal 12 10 over 10. Okay, this is our traditional measuring volatility. Maybe you call it like a moment. And this is our traditional, guys. And then we need to have LN methodology here. I mean LN our equal, I don't know, what is equal, blah blah blah. And estimating volatility is a maximum likelihood estimator of variance can be determined with if we assume the mean return is zero. Mean uh, return, uh, mean return is zero. Mean return is zero, and then yes, mean return is zero. Yes, estimating volatility, maximum likelihood, like an estimator of variance, can be determined if we have assume mean return is zero. This is statistic chapter. Then we have one formula here, guys. We have one formula here, and and O square and 1 over m and some operator m kill 1 u square and x and minus I equal, this is equal 1 over m operator 2. And then m is our number of observation, number of observation. And then this is 1, and then this is our return, this is secure and is a days, and then m over m. This is our maximum likelihood estimator, guys. And this approach weights each observation equally, guys. Okay, weights each observation equally. This is our parameter here to calculation method. If the goal is estimate current volatility, we may want to weight recent data more heavily. Okay, guys, more heavily. And then we have another estimating volatility approach. This is the exponentially weighted moving average model, guys. Okay, this is a EWMA, guys. EWMA. Sorry. Sorry. This is a EWMA, guys. Okay. This model assumes that weight decline exponentially back through time. Okay, decline exponentially, exponentially back through time. And this is our formula here: sigma square and lambda square and minus 1 plus 1 minus lambda and u square and minus 1, guys. What does that mean, this parameter? What is that mean, this parameter? This is easy, guys. This is easy. Weight on previous volatility estimate, guys. Okay, lambda is a previous volatility estimate here, n is observation, and lambda I also told you weighted previous volatility. This is our return, guys. Okay, this is our return nils, right? Return nils. Sorry for that. I told you n is a observation. No, bro, no, this is my bad. N is tomorrow, tomorrow, and minus one, of course, today, and weight previous, yes, lambda is a weight on previous volatility estimate, and it must be between 0 and 1. Okay, always remember this. Lambda have to be, sorry, has to be between 0 and 1, guys. Okay, now let's have a exponential weighted moving average here. Assume that the weight of previous volatility estimates, wait, previous previous volatility estimate is 0.97, and then what should I say, previous, this is a previous volatility is not estimate, and previous volatility estimate is 3 percentage, because if you want to calculate exponential weighted moving average, you should have previous volatility and previous volatility estimate, guys. Okay, and this is our previous volatility mean is accurate, and this is our estimate, and period return, uh, previous return is sorry, return is again 3 percentage, and then what is the EWMA model, guys? What is EWMA model? We already have EWMA model formula here. We should implement it. Um, we should implement it. This is our sigma and lambda, sigma square and minus 1 is a today, plus 1 minus lambda and u square and minus 1. This is a return, guys. I already told you this is a return. So sigma square and equal 0.97, because this is our um, weighted, sorry, previous volatility estimate here, and times 1 minus lambda here, 1 minus lambda, so 1 minus 0.97, and then this is our return, guys. Okay, this is our return. What was our return? 3 percentage, guys. 3 percentage, 0.003. Okay, that's sorry, 0.003 secure, because we have secure here, and it must be equal blah blah. I don't want to calculate it, but you should how you implement our formula and our numbers. This is EWMA, I mean average weighted moving blah blah blah. This is our formula, guys. Next time I'll give you some Python code how we need to calculate that and which library is available for us. But theoretical information is really important for us. And then we have GARCH model, GARCH model. What is GARCH? GARCH model, guys. I mean, GARCH model not only incorporates GARCH one. GARCH model not only incorporate the most recent estimate of the variance and security return, but also variable that accounts for a long run average level of variance and omega. Okay, variance and omega, guys. Okay, omega, and the sum of alpha and beta should be less than 1. Okay, alpha and this is our alpha and beta should be less than 1, guys. Always remember this in GARCH model. Okay, long run average, long run average variance level, long run average variance level should be equal omega over 1 minus alpha minus beta, guys. Okay, this is long run average variance level. By the way, we see YC is variance level and omega is a YC, guys. What does that mean? This is a variance level, guys. And a exponential weighted moving average, I mean EWMA, is nothing other than special case of GARCH. Volatility process with volatility process with omega equals 0 and alpha equal 1. Sorry, no one. No one. Uh, Sorry. Alpha equal 1 minus lambda and beta equal lambda, guys. All right, this is really important to understand. Please put in everything in your mind, and EWMA is nothing other than special case of GARCH. Okay, GARCH volatility process with omega equal 0 and alpha equal 1 minus lambda and beta equal lambda, guys. All right, and then the the sum of uh, alpha and beta is called persistence, guys. Okay, persistence. All right, this is important. Sum of alpha and beta is called persistence. So what does that mean? Alpha plus beta should be less than 1. This is sorry, this is covariance stationary. All right, stationary, and mean reversion exists. Okay, mean reversion exists. Oh, if alpha plus beta less than 1, this is covariant stationary and mean reversion exists. Okay, and alpha plus beta equal 1, what does that mean? This is easy question. No mean reversion, guys. Okay, no any mean reversion here. Always carefully when you have GARCH model. If you have alpha plus beta equal 1, this is not mean reversion. And then what should we say about this? The higher the higher the per persistence, to longer it takes for volatility to mean revert. Okay, the volatility mean revert, guys. I don't want to give you an GARCH example, because if I give you an GARCH example here, this video will be take a so long time. uh Next time maybe I have give you some Python calculation here. Mm. And then we should focus mean reversion here. I need to extend it for you. And mean reversion, this is important chapter. Volatility tends to exhibit mean reverting characteristic, and meaning that if current volatility is high and it is expected to decline, if it is low and it is expected to increase. This is a mean reversion, guys. If mean reversion is exist, long horizon risk uh, and resulting value at risk calculation will be smaller than uh, the square root volatility. Okay, smaller than root smaller than square root volatility, right? This is really important, guys. If reversion mean exists, if mean reversion exists, the long horizon risk will be smaller than square root volatility, and uh, then value at risk is increased, z score and sigma increase, guys. Okay, z score is decrease. And then that's all what I want to say about monitoring and calculation volatility. I'll told you I give it you information about GARCH and simple information about EWMA, and we did check it measuring volatility. Next time maybe I can give you stochastic process and volatility estimating in stochastic process. And you should know that I already give it you really important chapters here. What is volatility and how we can calculate it. By the way, EWMA, EWMA and GARCH is a econometric methodologies, guys. Okay, econ method. Machine learning and stochastic process is little hard, but they have some assumption here. You should know mean reversion, GARCH, and division from the normal distribution chapters here. Thanks for watching me. See you next time, guys.